Hi, I'm Ariana, and this is Lab 6 Magnetic Molasses. So the purpose of this lab was to observe the effect of Faraday's law on a bar magnet falling through a tube of aluminum foil, and then to model that tube-magnet interaction computationally using GlowScript, and then compare the real-world observations to the model. So some physics principle used was an understanding of magnetic field of dipoles, magnetic flux, Faraday's law, magnetic force, and Ohm's law. And the results, the real time it took for the magnet to fall through the tube was 1.13 seconds, and the time it took for the computational model was 0.764 seconds. So the physics principles for this lab, first, the magnetic field for dipoles. Derived from the Biot-Savart law, we can see this formula is the magnetic field for a dipole on or off axis, where mu represents the dipole moment of the bar magnet. For magnetic flux, it is the integral of b dot n hat, where n hat is the unit normal vector dA, where dA is change in area. Faraday's law is essentially that an induced current will be generated when there is a change in flux. So the EMF equals the negative of the derivative of flux over time. A magnetic force from a current is IL cross B, and Ohm's law says that voltage equals current times resistance. So the experimental procedure for this lab was first to find the north pole of the bar magnet and note it down using the magnetometer app, then place it above a tube and drop it into the tube. Repeat this procedure 5 times and then average the 5 measurements for how long it takes for the magnet to fall through the tube. So that is a video of us doing that. In our experimental data, the average time for the magnet to fall was 1.13 seconds, and the times for each trial is also shown. For the computational model, first you can see us initializing the constant. The magnitude of mu was derived from the last lab, and it was 2.81. Then we visualize the bar magnet. This function dipole B, essentially returning the magnetic field of a dipole given by the formula. Then this function calculates the change in flux over time for a magnet and a ring a certain observation distance away from the bar magnet. Then we find the force due to gravity, which is listed here, and then there is another loop which essentially calculates the flux, the derivative of flux, and therefore helps find the induced current in the ring based on the bar magnet falling and its velocity. So now we can find the magnetic field at the position of the ring, and then find the magnitude of the force on the bar magnet. So putting it all together, we have the magnetic force calculated, and then the net force, which is just gravitational force plus magnetic force, and then the bar velocity, which will decrease because it's going down, based on the acceleration, which is based on the net force. So net force divided by mass times change in time, and then the position, which will also decrease based on the velocity of the bar, as you can see here. So this is the actual model results. You can see the bar magnet dropping through the tube and the velocity versus time graph, which is nonlinear. So the blue ring represents a counterclockwise current, and the red ring represents clockwise current because flux is increasing for rings under the magnet as the magnet is falling, and the flux is decreasing for those above it. So the direction of the induced current is going to occur accordingly. So the time it took was 0.764 seconds, which you can see here. Some sources of error, there could have been other magnetic fields. The initial velocity could have been higher than 0 in the real world. There could have been measurement errors, and there could have also been air resistance and drag, which we didn't account for. So the results are as follows, and for conclusions, the real world time was about 0.3 seconds larger than the simulation time. The velocity versus time graph, as we just saw, was nonlinear in the simulation. The slope of that graph decreased with time, and velocity became constant, which means that the magnetic force approached the gravitational force in magnitude. So what if the resistivity of the conductor was reduced to become 0? So if the resistivity was nearly 0, the current of the ring would increase greatly by Ohm's law. because the EMF would remain constant and resistance would decrease, therefore current would increase. So the magnetic force on the bar magnet would increase and the magnet would drop much slower and therefore accelerate much faster because F equals IL cross B. So if holes or slots were cut into this tube, it would affect the ring currents in the model because it would decrease the induced current. And therefore, the induced magnetic field and force would also be decreased, and thus the bar magnet would fall much, much faster.